Thank you for the kind introduction. Hello, everyone. I will be presenting our work on modeling concrete under the mesoscale, in particularly fiber-reinforced concrete. Although concrete is modeled as a homogeneous material on the macro scale, it is in fact a highly heterogeneous material. It consists of aggregates, sand, of course cement, and in the case of fiber-reinforced concrete, fibers. We are interested in modeling concrete on the mesoscale, where we should resolve fibers, air bubbles if they are appearing, and coarse aggregates. Why we want to do so? Because the behavior of concrete, or in particularly fiber-reinforced concrete, is governed by this complex interaction that happens between these ingredients at the mesoscale. So the thing is, traditional experiments cannot help us see this interaction. So our vision is to create a virtual lab where we can generate specimens with different ingredients and see the behavior happening on the mesoscale. So our vision for a virtual lab consists of two modules. The first one we call model generation, where we create finite element models starting either from synthetic data or from real imaging of real specimens. And the second module, of course, is to simulate the fracture response, to mechanically break them. Today I will be focusing on the model generation module. So our aim is to start with some synthetic data and end up with a trustworthy finite element model. But also in some applications we would like to validate our model. So we would like that we would be able to start from a CT scan of a real specimen and compare it to our workflow. So we have already in our group, we have published a software called the Concrete Mesoscale Generator, or CMG for short, which is an open source software that lets the user assume some parameters about concrete, like the sieve curve, the size, volume fraction, and the output of this software is a voxel image of a synthetic generated micro or mesoscale concrete. Similarly, we created a program that generates a cocktail of fibers, also synthetically, but this is still a work in progress. It's not yet published. However, if we want to start from a CT scan of concrete, if we take a look on a cross-section of a standard fiber-reinforced concrete, it's quite trivial to segment the pores and the fibers because of the different attenuation factor to the cement and aggregates. However, segmenting aggregates from the cement is not so easy, and we can use more advanced techniques like active contouring, for example, which works well in our case. However, once we have the segmented image, the story does not end here. If we segment the fibers, for example, we see that most of the fibers are touching. If we get the voxels of the fibers in isolation, we see that they are touching. And we have to resolve this touching. We want to get every single fiber so we can model them. If we apply template matching, it would be expensive. You can imagine how expensive that would be. So we developed our own algorithm. We use skeletonize, and then we can easily identify the branch points. You can see them in blue here and here. By deleting the branch points, we can end up with individual segments. These segments, we can compute their direction by computing the principal directions, and we can, by comparing the directions of every single segmented piece, we can reassemble a fiber, and then by connecting the endpoints, we can have every fiber as it should be. But this only works for straight fibers, obviously. The same goes for aggregates. Once we segment the aggregates, they are also probably touching, and we want to separate them. So we can either use watershed, some morphological image processing. This is I would have to say this is image specific. Depending on the quality of the image, you have to manually step inside to see which parameters works best for you. For me, watershed algorithm works very well. Now, I've been talking about imaging so far. We want to go into geometry now. If I have an image of either an aggregate or a void, air void, I want to convert it to geometry. There are many options. One of the best options I've seen that works for me so far is convex hull. Although I lose a little bit of the actual shape, but if I have a high quality image, it's more or less the same unless there are convex aggregates, which are mostly not this case. So convex hull works very well for me. There are other methods like alpha shape method or some surface smoothing method, which also work. The thing is, because I am triangulating every inclusion in isolation and then assembling them together, it's quite often that we see that the triangulations of these inclusions, they intersect. I can solve these intersections by applying Boolean operations, which will be expensive, of course, or I can try to I perform ray tracing algorithm where I check every inclusion with its neighbors. And when an intersection is detected, I can fix it by either shrinking the aggregate or just deleting some parts of it, like this. Now, I have the geometry of the inclusions without intersections. I want to now build a model. Let's say my model is a cube. So I build a cube, triangulate the surface of the cube, and then put the aggregates or air bubbles inside. This is no problem. I can pass this structure to any measure, and I will get very nice results. No problem. But the thing is, as if I don't have the aggregates that are touching the surface, in some applications, this area without aggregates on the sides might give me bad spurious results, depending on the application. So if I want to put the aggregates that are actually touching the surface, I see I have a problem because I have surfaces that are intersecting. Any measure would reject this immediately. Boolean operations are immensely expensive. It takes days just to fix this issue. Because subtracting a triangle is okay, then the second operation is a little bit more expensive than the third. It gets exponentially more expensive because you have more triangles. So one way to fix that is, instead of triangulating the cube with the base triangles I have, I now retriangulate the cube with constraint Delaunay triangulation, where the constraints are the aggregates themselves. And this can be done in seconds instead of days. And now I pass this structure that looks like Swiss cheese with holes on the surface and inside to a measure, and I can get very nice measures. I use Tedgen, which is very easy, very nice and easy to work with through an interface. So to go back to my CT scan, this is the original CT scan, and this is my segmentation. You can see aggregates are shown in red, the air bubbles in blue, and the fibers are thrown in the mixture. And this is how the mesh looks like. I can get good quality meshes with this. But this is not my goal. Our goal is to have a unified program that generates finite element models synthetically. So the user should be theoretically able to specify some parameters, wait a few seconds, and get a model. The user should be able to control the mesh and not just be restricted to cubes, but cylinders as well. But this is still work in progress. Now, the second module is mechanical simulation. We are interested in, as I said, in the cracking behavior of concrete. So to model cracking, we use interface elements. These are elements that are zero thickness elements that are inserted between the bulk elements. And they are equipped with, you can equip them with, instead of traditional plasticity law, you can equip them with the cohesion law, which is a traction separation law. And we also to take friction into account, we also include the frictional sliding law. And because we are talking about, we want to model cyclic loading. If you are modeling monotonic loading, you don't care about cracking closure because you open the crack once. But if you open the crack and you want to close it again, it will not close in the exact same configuration as it used to be before, because some debris will be bridging the crack and will not allow you to close it. So we want to model this so we can have the hysteresis in the load displacement curve. And this can be easily modeled by introducing a one-dimensional elastoplastic load to the interface element. I will not go into details to this. Now, when we talk about interface elements, one drawback is notoriously known for interfaces, which is the computational cost. Because if you put an additional element between every two finite elements, this will cause the mesh to be exponentially larger in terms of number of degrees of freedom. But what we do is we insert interfaces adaptively only when and where they are needed during the analysis. And this allows us to get like 20 times faster simulations in 3D. So we kind of solve this problem of interfaces. To model the fibers, we model them discretely. We don't homogenize them in the material, but we want to model them as they are. So we discretize every fiber with standard Lagrangian Timoshenko beam elements, the standard beam formulation. And every beam element is tied, we check where it intersects the background mesh, the bulk element, and then we introduce bond elements, which dictates the relationship between the fiber and the cement, which is embedded into. This bond element has a penalty-based frictional law to take friction into account also. And the fiber itself, sometimes we see that the fibers are breaking during the simulation, so we had to introduce a plasticity law in the fiber itself. It's a simple von Mises plasticity law. Now, this is a test where to validate our fiber model. It's a notched prism specimen. The fibers in this region, we have generated synthetically some fiber mixture, and when we compare it with the experiment, we are in very good agreement. And you can see here the hysteresis. They are very thin, but these hysteresis are not due to contact. These are hysteresis coming from what fibers can carry due to tension. There is apply tension and remove it. Now let me show you the specimen I showed at the beginning. This is a very small cylinder. It's like 4 centimeters in height, and this is our model. We broke the specimen a few months ago. We are in kind of good agreement with the experiment, and this is the real one before and after, and this is our simulation. We are trying to get the exact same cracking, but it's not so easy. If we take a look on the before and after, this is the real one. This diffusive cracking is known for high performance concrete. In normal concrete, you see cracking only around the aggregates, not the aggregates themselves breaking, and this makes our life more difficult. By comparing our results, they are not. Well, it's okay, I would say. but this result is 2 days old. We got it 2 days ago, and we are still working on it. So to summarize my presentation, I presented our vision for a virtual lab. It's still a work in progress. This has been all built in our department, and we still have to validate our models, whether it's the model generation or the mechanical simulation part. And once we are happy and confident with the model, with the framework, then we can try to test out hypotheses like, is short fiber better than a long fiber, or different shape of aggregates, how does it affect on the micro scale? Thank you very much for your attention.